Good day, guys. Welcome to Ray Engineering Mechanics. So, here is a question on equilibrium of a rigid body. So, the question says two links A, B, and D are connected by a bell crank as shown. Two link A, B, D. So, those are the two links are connected by a bell crank. So, this is the bell crank as shown. Knowing that the tension in link AB is 720 Newton. So, as you can see, the tension in link AB, this is AB, so the tension in this AB is 760 Newton. Now the question now says determine A, the tension in link DE, so we have to determine the tension in this link, and B, the reaction at C, so we are determining the reaction at this C. So since this is a equilibrium of rigid body question, so let's first of all draw out the free body diagram of this. So then we have this to this point, then also to this point, then we are having this in this manner. So this is our D, this is E, this is C, sorry, okay, let me put it here, C, and this is A, this is B. Now let's write out all the forces in this particular case. So now, as you can see, this particular length AB is having a tension here. Let me use the red pen to indicate the tension. The direction of the tension is in this sense. Now, this particular C, as you can see, this is a pin, like a pin or an hinge. As you can see, that means we are having two reactions at this edge. So that means we'll be having one in this sense, the other in this sense. Then we are having a tension in this D, so that means we are having a tension here now. So as you can see, since we've already drawn the free body diagram of this particular system, and we know the tension in link AB is 720 Newton, then the length from here to here is the point. So from here to here, we know the length, and also we know the length from this upper part here to this down part. Then we also know the distance. Okay, let me use this in this scenario. We also know the distance. So from here to here is 80 millimeter. Also from here to here is 120 millimeter. So, and the question says the angle here is what? 90 degree. Now, as you can see, so in this case, since I've drawn the free body diagram of this particular system, now don't forget this is a 2D equilibrium question. So now let me take the way I'm going. Let me write out the way I'm going to be taking my my stuff. So let's say we are using this dimension, so in this sense, so that means this is my y, this is my x. So now as you can see, this D is going in y direction. This C we are having, so let's say this is our cy, this is our cx. Now in this case, that means we can actually resolve the one at B to be in this type of dimension. Don't forget, we can't call this a y, we can't call it neither y nor z nor x. So we can actually resolve this. So in this case, let me bring out ABC. Let me split it into two. Let me bring out ABC. So that means I'm bringing out my ABC. So that means I'll be having something in of this manner. So I'm bringing out this. So that means I'll be having something of this manner. I'll be having something of this manner. Yeah. Yeah. Now, this is 90 degree perpendicular to each other. So now let's make this in this dimension. So that means, let me use red. So that means we'll be having something like this. Let's create this thin line. So that means we'll be having something like this. So that means this is how our tension is moving. Tension in this is moving. Okay. So as you can see, let me label it. This is my A. This is my B. Sorry. Don't forget, this is a tension here, like from A to B according to the diagram. The tension in this case will be pulling it downward. Sorry. So that means our tension here is going in this sense. Sorry. As a mix up. Also here in D is going in this sense. But if you do it the other way, you will be getting a negative answer, which will be indicating that it is in opposite direction. But let's follow this. This is going in this sense. So this is going in this sense. So that means our action here, it will be in form of this in this direction for Y. Now this in this direction for Y. Now most of you might be wondering that why do I know that this direction, this force here is going in this downward direction, these two forces? The reason is, don't forget, according to Newton's third law of motion, it says for every action there must be an equal opposite reaction. Don't forget, this particular two tension, if I said they are acting downward, that means this reaction here is acting upward. And if I said these two are acting upward, that means the reaction here is acting downward. That's the reason why for every action there must be an equal opposite reaction. Newton's third law. That's so in case you are using the upper reaction, that means this reaction here will be acting downward, and this one will be opposing this. So that's why. So since I've actually resolved this into this now, and I know the length here to be, let me use this. The length here to be, let me convert it, 0.06 meter. Then also I know the length here to be 0.06 meter, and I know from here to here is 0.6. From here to here is perpendicular. Then, and we know from here to here, like the distance here to here, to this point, is 80 millimeter. So that means from this ground level here, this spot here, to this spot here in downward is what? 80 millimeter, which is the same thing as 0.08 millimeter. And we know from here to here, this will be what? 0.06 meter. So that means in this case, let's call the angle here theta. So that means we can actually calculate this angle theta to be able to resolve this. We can actually get this angle theta. So that means from here we know our tan theta to be equals to your y over x. This is your y, this is your x. So then we know this will be 0.06, which is the same thing as all over 0.08. So that means our theta will be equals to, so let's do this, 0.06 over 0.08. So that means we have shift and arc of the answer. So that's 36.87 degree by approximation. So that means we're having 36.87 degree. Now, for better understanding, since we already know, that means we've already calculated the angle theta here to be 36.87 degree. Don't forget, this is our y-axis in this sense, and this is more like your x-axis in this sense, because we are following this dimension. So that means here is perpendicular, here is 90 degree. So that means if here is 90 degree, here will be what? 90 minus this theta, which will be, so that means our answer will now be 90 minus 36.87. So that means the angle we are having here is what? The angle here, let's call it alpha, which is what? It will be 53.13 degree. So that means our alpha is 53.13 degree. So that means if this is 53.13 degree, here will be what? Since don't forget according to the question they say here is 90 degree. So that means here will be also be what? 36 point, let's call it beta. So that means our beta is equals to 36.87 degree for our beta. So that means since we've already done this in this direction, so we can actually resolve this into into components. The tension here, don't forget that we are dealing with the tension here. So that means we can actually say for our Ty, it will be your tension times, now don't forget this will be your x, this will be your y. So that means, let me bring the diagram out in another sense. So that means, sorry, let me bring it out in another sense. So that means you will be having something of this manner. Here is your theta 53.13 degree. So this will be your x, this place will be your y. So that means your y, this will be your tx, ty. Let's put it like that way. So that means our ty will be, this will be adjacent. So that means we'll be having cos of beta. Then your tx will be t sine of beta. Don't forget we've actually resolved that into its component. So that means we've resolved this tension into its x and y component. So the way our new free body diagram will now looks like, it will now looks in this manner. So let's redraw the free body diagram to indicate all this that we've done. So that means we'll be having this, which is our f. So we'll now be having this as our points here, and we'll be having this here with the tension. I said it is acting downward here. Also the tension here, I said, is acting downward here. Then don't forget I split this. So that means we'll be having our ty in this manner. Then we'll be having, sorry, tx in this manner. Then that means we'll be having our ty in this manner. Your tx will be going also in this direction. Your ty will be going in that direction. Then your cx will be going in this manner. Your cy, okay, we are using the same pen, sorry. Your cy in this manner. Your cx, for better clarification, your tension here in this direction, your tension here in this direction, then also this in this direction. So tension here in this direction. Then we have this, which we actually split into this. So that means we already know from here to here, from here to here is 80 millimeter. Then from, we know here is 53.13 degree. Then from here to here it is 120 millimeter. Then from here, sorry, from here to here is 90 millimeter. Don't forget what this is saying, from this point to this point. That means here also is 120 millimeter. Now don't forget, in this case we are having three equations. Don't forget, we will be having summation of x. We have three equations and we are having how many unknown? This is one, the tension, 1, 2, 3, 4. Like you're having 1, 2, your ty, your this, but we can call this tension 1 since we've actually resolved this, which is 1. You're having 2, you're having 3, which is we'll be having 3 equations, 3 unknown. So that means we'll be having summation of fx to be equal to 0, summation of fy to be equal to 0, summation of moment about this point here, let's call this point C, which is C, to be equal to 0. So those are the 3 equations that we need. So now, before we now go about it, let's first of all start with the moment. Now, we want to take our moment, and we know taking moment, our moment is the product of force and perpendicular distance. So the first thing is we have to look for the perpendicular distance of each force. Now don't forget that this particular force, which is 19 meter, which is our DE, which is unknown, TDE, this is our tension DE. We have to look for the perpendicular distance of this force. Don't forget, this force is going in y direction. The line of action of this force is also in this direction. This force can actually reach here. Are you with me? So that means the perpendicular distance of this force is this line, is this your 120. Now for your tx, don't forget this is your tx. Your tx, this is your ty. Now for your ty, the perpendicular distance of this your ty is from this point to this point. From this point to this point. That's meant for your ty. Then your tx. So let's just resolve this. Since we've actually done this, so now let's now go about the resolution of this your t. Don't forget, we already know this is our a, this is our b, this is our d, then this is our e, then this is our c, point C. So now let's first of all start the summation of force of x to be equal to 0. Since we've already identified our equation, so now let's start the summation of force about x, which is equal to 0. That means our summation of f of x is equal to 0. So that means in this case, so now let's resolve these forces in x. Don't forget we are having our tx, which is t sine beta. Now don't forget this tx is going in opposite direction, which will be minus t sine of beta. Then your cx plus cx. Don't forget we are not having any tx in this direction, so is equal to 0. So that means our cx is equal to t sine beta. So that means our cx is equal to 720 times sine. Your beta is what? 36.87, which should be equal to Newton. Now let's resolve our summation of f of y, which is equal to 0. So don't forget we'll be having this, it is coming in downward direction, which is your ty, which is t cos beta. So don't forget downward direction minus, then your cy going upward plus cy, then your tde, which is coming downward, minus the tension in de, which is equal to 0. So that means our cy is equal to tde plus t cos beta. So that means our cy is equal to, what's our tde? Our tde, which is unknown, plus your t cos beta, which is 720 times cos of 36.87, which is 576 by approximation. So let's call this our first equation. That means we'll be having this as our equation. So now let's take the moment about C. So you know summation m about C, it should be equal to 0. So now with respect to your TDE, so that means don't forget the moment about this particular CX and CY is equal to 0, because that's the moment about the point. Those two forces are acting at C, so that's 0. So about TDE, this is our TDE, this is the perpendicular distance of this. So that means we'll be having TDE times 0.12 in meter. Now this is coming in this direction, so let's take our counterclockwise direction to be positive. So that means this is coming in this direction, which is clockwise. That means this will be negative of this. Then the next one, we are having our ty, which is coming in this direction. So let's say our ty times the perpendicular distance, which is this, which is 0.08. Now we are taking the moment in this direction, which is positive, counterclockwise direction. Tx dot 0 times 0.06. Don't forget, this will be coming in which direction? Also with the direction of this force, this direction, which is counterclockwise, plus should be equals 0. So that means our TD 0.12 TD should be equals to, now your Ty, which is 576 times 0.08, 576 times 0.08, that's 46.08, plus now your Tx, which is 432 times 0.06, which is 25.92. So that means our TDE will be equals to 25.92 plus 46.08, that's 72, divided by 0.12. So that means our TDE is what? 600 Newton. So that means the tension at DE is what? 600 Newton. So we can now go back to this our equation. We know our Cy, this is equation 1. So we know our Cy to be equals to TDE, which is 600 plus what? 576, everything in Newton, which is equals to what? So 600 plus 576, 600 plus 576, which is equals to 1176 Newton. 1176 Newton. Now, don't forget, we've actually gotten our Cy and our what? Cx. So we can actually put this out. Don't forget, we are looking for the reaction at C. The reaction at C will be in this direction. So that means we look for the resultant of our Cx and our Cy. So that means we are having something like this. Your Cx, your Cy, Cx, then this will be your what? Your Cr. So that means this is your Cx, which is 432, and this is your Cy, which is 1176. So we can look for the resultant. So that means we know our Cr to be equals to the square root of Cx squared plus Cy squared. So that means we know our Cr to be equals to square root of 1176 square plus 432 all square. So now let's calculate this. So that means we are having the square root of 1176 square plus 432 square. So that means we are having our Cr to be equals to 1253 Newton by approximation. So that means the reaction at C, is equals to 1253 Newton. Then tension at DE is what? Your 600 Newton. Now don't forget, this particular thing will be inclined at one angle. Let's call it gamma. So we can actually look for gamma. So that means, and we know tan gamma is equals to y over x. So that means we can just see our gamma will be equals to shift tan arc of your y, which is 1176 over 432. So that means your gamma will be equals to shift tan arc of 1176 over 432, which is 69.83 degrees. So that means the angle between your Cr, your resultant force, and the x, the force at x, your reaction at x, is what? 69.83 degrees. Thank you very much. Here comes to the end of this particular question. Thank you very much, guys. Make sure you subscribe to my YouTube channel and always turn on the notification button.